Good afternoon, all. Thank you so much for joining the webinar. We will be presenting in just a second, and I will introduce our speaker, Professor Tim Wright, and a little bit about us. So thank you so much for joining. My name's Yusuf. I'm Head of Sales at SatSense, and presenting today is Professor Tim Wright, who is co-founder and director at SatSense, but is also Professor of Satellite Geology at the University of Leeds and Director of COMET. Tim has pioneered the development of InSAR for the measurement of tectonic deformation due to continental collision and magmatic rifting. Tim is a preeminent academic in the field of InSAR and founded SatSense in 2018. And this presentation is focused on some of the work that we've done in and with water utility companies. Without further ado, I will hand over to Professor Tim Wright, but a couple of housekeeping rules. If you can ensure your camera is turned off and your microphone muted, that would be fantastic. There will be space for questions at the end, so please feel free to pop them in chat or open it up for people to raise their hands at the end of the session. For us to have some questions. This is being recorded and we will send the slides out afterwards if you'd like to refer back to them. Without further ado, I'll hand over to Professor Tim Wright.
Thanks, Yusuf, and thanks everybody for joining. It's a great pleasure to be here today to talk not about earthquakes and volcanoes, but to talk about some of the work we've been doing in SatSense, and in particular some of the work that we've been doing kind of focused on pipelines and working with water utilities in the context of some work funded through the European Space Agency and some collaborations with a few different water utility companies. So first of all, who is SatSense? So as Yusuf mentioned, I co-founded SatSense with my colleague Andy Hooper in 2018. We spun out of the University of Leeds based on the work we've been doing using satellite radar to measure ground deformation. And we realized that as well as being able to measure the kind of big scale deformation due to plate tectonics and volcanoes that may or may not be about to erupt, we could see much smaller scale detail that had a relevance to sectors such as the water utility sector, or to homeowners, or to network providers like Network Rail, or the highways agencies. So we've got something like 80 years of combined experience within SatSense working on InSAR, both for myself and Andy. We've got a lot of PhD students, former PhD students in the group. Something like half the company have a PhD, many of them from our group. There's a lot of expertise there, and we're really growing very strongly, particularly in the UK, but also increasingly working overseas as well. And our focus has been really about making InSAR data accessible to people with a wide range of backgrounds, for a wide range of applications, and as well as making the data accessible, also making it useful. So making sense of the data. What can we do with it? What does it mean? How does it help us solve problems in the real world? So first of all, if we just think about what the technology is, so InSAR is Interferometric Synthetic Aperture Radar. And essentially, this is a diagram that's not to scale. So this is the Sentinel-1 satellite, which flies at about 700 kilometers above the Earth. And it sends radar waves with a wavelength of about 6 centimeters down to the ground, measures the energy coming back. And what happens is, if we go on repeated passes of this satellite, you can measure any very small changes in the position of the ground, because they cause a change in the phase of the radar wave that we see. So essentially, it's a very precise way of measuring how the distance between the satellite and the ground changes through time. And that can give us insight into how the ground is behaving, whether it's subsiding, whether it's heaving, and actually in some cases, whether it's moving laterally as well. We get something like 1 millimeter per year precision with the data, with a spatial resolution that ranges from about 1 meter with the very high resolution satellites to about 5 by 20 meters with satellite systems like Sentinel-1. So just to talk you through the workflow, you don't just download an InSAR product straight from the satellite. So the satellites are in these polar orbits. They're acquiring data every time it revisits an area. With the Sentinel-1 system, the constellation, when it's fully operational, has 2 satellites, which means there's one image. It repeats every 6 days on that same track. So we acquire data, we build up a stack of those images, and then the clever part is here. We're basically building algorithms that can extract this precise ground movement information from those big stacks of radar data. And there's a lot of the IP goes into this. And then once you have those reliable measurement points, you can produce maps of the velocity, but you can also think about tailored indices. So, is a point accelerating? Is an area bending? Is the movement that's likely to cause a pipe to fail, for example? So a time series InSAR product would look something like this. So here's our stack of images. We then go in and produce those, and within our SatSense system, you can go into our interactive portal, zoom in on anywhere in the country, and you'll see a set of dots like this. And basically the idea here is if they're white, if there's a dot at all, it means we've been able to extract a ground movement information, and we can't do that everywhere, as you can see here. But where we've got white information, that means that ground is stable on average. If it's red, then there's movement away from the satellite, and if it's blue, it's movement towards the satellite. Now, this is the town of Ripon in North Yorkshire, not very far from our headquarters in Leeds. And this is an area that sits on gypsum, and it's prone to sinkholes. And if we just zoom in on this area here, this red blob here, we can see that there's this area, very, very tightly defined area of subsidence. And if we look at any of these individual points, we can extract a time series of the ground movement. And here you can see that from the start of the Sentinel-1 time series, which was in 2015, we ended up with about 10 millimeters of subsidence by mid-2018 here, and then an acceleration at this point. And if we just look at that time here, this kink here in August 2018, around about the point of this kink in the time series, this is what happened. This sinkhole opened up underneath the Sainsbury's in the centre of Ripon. So what you can see with this data is that we're tracking that long-term movement before the sinkhole actually opened up, as well as some more rapid movement after the sinkhole opened. So what can we do with InSAR? I showed you one example there, but the idea is we can determine whether an asset is at risk due to movement. We can then monitor and alert if there's new movement of the ground or structures, and this then leads to being able to make smarter decisions, whether that's more cost-effective designs, whether that's implementing a regime to make your railway embankment more stable, or whether that's deciding which of the pipelines in your portfolio of pipelines are the ones that you want to target for maintenance. And in particular, if we can also identify, as well as the areas of movement, the areas that don't move are also that's quite valuable information, because you can direct resources away from areas that are stable, showing as stable in the data. And we can see features ranging from individual properties here up to the scale of bridges. This is an area in London, one of the bridges across the Thames, with some subsidence that's been due to the recent tunnelling due to the Thames Tideway project, which I'll show you a slide on later. And this is a landslide, a big landslide in Folkestone. The railway line actually runs down here along the base of this landslide, and you can see you've got subsidence at the head of the landslide and some heave at the bottom of the landslide, and those colours in blue. So the whole of that slope is rotating and falling down the hill into the sea, which is obviously a problem for Network Rail. Few things that you need to know, useful to know about InSAR. It's not an off-the-shelf product, so actually creating these reliable results requires significant algorithm development and processing, and there are a number of commercial providers out there. We all have slightly different algorithms. Of course, SatSense is the best algorithm, of course, but there are many very good algorithms out there. as is based on lots of scientific publications over many years. Andy and I have been working on this since the late 90s, early 2000s. InSAR doesn't work everywhere. I mentioned this earlier. Essentially, what it relies on is having scattering properties in a resolution cell. So for Sentinel-1, that's about 5 by 20 meters on the ground. It relies on those scattering properties not changing significantly. So you can see here, for example, there are agricultural fields where we're not getting measurements, and that's because if the farmer plows their field, then we're going to lose the signal. It's going to move all those individual radar reflectors around within that field. So where it does work well is in these urban areas, these built-up areas, these places where there are buildings, and also places in the natural environment where there's bare rock or very little vegetation. You can see on the cliffside here, we're getting some patches, and on the foreshore where we're getting some quite good signal. For the pipeline applications, of course, many pipelines are located in places where people live. So actually the coverage of InSAR data actually maps the locations of pipelines pretty well in general. And we have a solution that I'll talk about later in places where we don't get natural coverage. But we don't need to put instruments out here. We're relying on where the radars are naturally reflecting from points on the ground. And so it's a really powerful technique in allowing us to make these measurements in a non-invasive way without needing to put instruments out there. And we can also, when we look back in time, we don't need to know we have a problem, then go out, procure a monitoring solution, install some instruments, and then wait for those instruments to collect data. We can instantly go back and look within the Sentinel record back to 2015, and there are other satellites we can go back further in time if we need to. Having said that, I think it's worth saying that these InSAR time series can only be updated a few hours after a new satellite acquisition. And with Sentinel-1 system, there are 2 satellites. Each of those satellites acquires data every 12 days. So in a single orbit, we've got data every 6 days. You get data as the satellite goes north and as it goes south. And in the UK, you get a lot of overlap. So in practice, when we have 2 operational satellites, there are 8 acquisitions every 12 days for most of the UK. But it's not the solution for identifying rapid infrastructure failures on the timescales of minutes to hours, even a few days. It's going to be the wrong solution for that. What it can do is identify sites at risk of failure due to long-term movements, and also identify places where there might be changes in those rates of long-term movements. So we do some work, for example, monitoring bits of infrastructure for Network Rail and for some of the water utility companies, where we're actually monitoring these sites, looking for changes in those rates of movement and providing alerts. And I'll show you an example of that again later. As I mentioned within SatSense, really what we're trying to do is make those data accessible and useful for people. And we do that in a number of ways. One is we do very large scale processing, and our algorithms are unique in being able to process large areas and keep them up to date all the time. So I'll show you, we do the whole UK, we process the whole of New Zealand, keep those areas completely up to date, and we're able to roll that out to other areas in the world. And because they're pre-processed, those data are then instantly available. So in terms of a solution for accessing data, you can get those data straight away, and they're always live and as good as they can be. But I think a lot of what we've realized when working with SatSense is actually working what with customers. What people want is a solution. They want to know which of my pipes are likely to fail due to ground movement. And so we've been doing a lot of work in terms of taking the data, deriving products from it, using machine learning to develop risk models, and trying to come up with solutions for customers. Sometimes people want data in different ways, whether that's ingested in their own system. So our data now goes into the Network Rail monitoring system, into their portal. They have API access to our data. Other customers would like self-service portals to access the data. and say other customers would like solutions. Which of my pipelines is the most likely to fail? We have novel algorithms that are computationally efficient. We do rapid updating of large areas, and we get a high measurement density. So these are some of the characteristics of SatSense data and some of the things that we do a bit differently to other customers. So if we think about the UK, I mentioned we process all available Sentinel-1 data over the whole country, and we have that pre-processed from 2015 to the present day. This is updated whenever new satellite data gets acquired. There are something like 700 million data points, measurement points in the UK, each of those with about 350 or more measurements going back to 2015. And so that gives us millimeter precision with a spatial resolution that's approaching sort of property level. Sometimes, however, that's not enough, and we can also work with higher resolution satellite data. Sentinel-1 is free, and it is made available from the European Commission. So this is a data set we are able to do this mass processing on. With the high resolution data, you have to pay often quite significant sums to buy stacks of data for a given area, and what you get from that is a higher resolution product. As you can see in this comparison, this is data from an Italian system called Cosmos SkyMed compared to data from Sentinel-1. Actually, they actually both show the same linear feature running through here, which is the Thames Tideway super sewer, and one of the on-land spurs of that, just at its western end. You can see they both show essentially the same feature, but you get a lot more measurement points with the high resolution data. And I couldn't resist just showing you this slide because it's just a little bit more detail about what the kinds of information you can extract from these high resolution data sets, but also from Sentinel-1 in some areas. So here's that line showing very clearly where the tunneling has taken place. I don't know whether this still counts as a pipeline, by the way. That's my question for you, or whether this is no longer a pipeline. It will have sewage running through it, so it's a pipe, I guess, but it's a very, very big pipe. But what we can see here is if you monitor the ground above it, if you take one of these time series, again, this one starts in 2019, goes up to 2022, and this is the time series, and you can see that there's a little drop down. It's flat here at 0, and then later in the time series we're down at -10 millimeters, and you can see that drop happens in this relatively short period of time in March 2020. And as we move along the pipe, you can see the period when that drop happens changes. So this point drops in June 2020. Here we are in July 2020, August 2020, September 2020. So we're able to track the progress of that boring machine under the ground here as that tunnel is in place. You can also see that you're getting information about some of the geomechanics of the properties here. So in some of these locations, the drop happens like this first one fairly quickly, and it's basically steady after that. In others, there's a longer tail of slower subsidence that happens after a smaller initial subsidence. So this must depend on the soil conditions, for example, and the shallow subsurface there. So I want to focus a bit more in the rest of this talk about some of the work we've been doing with water utility companies, and that's been in the context of a project funded through the European Space Agency called DRIPIN, and I can't actually even remember what the contrived acronym stands for anymore. But I think with some of these funding agencies, if you don't have a really good acronym, you've got no chance of getting these things funded. So this one's called DRIPIN, and we initially had a feasibility study funded, and that was working with Northumbrian Water and with Severn Trent Water. And the goal really was to integrate ground movement data into the water utility workflow and decision making. So we worked with those water utility companies. We focused on pipe failure risk management, but also explored operational integration. The idea was to determine how to integrate ground movement data into the water utility workflow and decision making, and then to do some modeling to assess the value that the InSAR data provides. How does it improve our decision making? So, as many of you will know, there's obviously large underground pipe networks that water utility companies have to maintain. Bursts are costly, both in terms of repair costs, as well as in terms of compensation and performance penalties. But budgets only allow a replacement of that's below about 1% a year. And at the moment, strategic maintenance decisions are primarily made based on network properties alone. And of course, a lot of repairs happen when you have failures. And it'd be much better, of course, to replace things before they fail. So we explored in Dripping how ground movements correlate with pipe failures. So we were able to produce simple results like this, showing actually here's some ground movement, and here was a pipe failure. So this was a fairly early result. And again, you can see the pipe failure is happening here, not at the location where you've got maximum movement, but where you've got bending in the pipe, which obviously makes sense in terms of the mechanics. So how do we map the InSAR data then onto the pipe network and do better than just these simple sort of one-off comparisons? We can look, this is some work we've done with Sydney Water in Australia, an area here in one of the suburbs of Sydney with some significant ground movement. What you can do is take those InSAR data, and you can take a number of classifications of that and map them onto the pipelines. Here we've just done a red, amber, green rating of those individual pipelines. And then if we look at historical failures in this area, again, you can see a good correlation. Most of these failures are happening in areas we've mapped as red or amber on this scheme. But again, we'd like to do better than this. So one of the things we've been developing is a number of risk indices. So as I mentioned, if the whole village is going up and down, it probably doesn't affect your very local pipe movement. So things like bends in the ground, and things like accelerations or the extent of seasonal movement due to clay shrink swell. These are features that perhaps are more likely to correlate with pipe failures. So what we've been doing is looking at a whole bunch of these indices and testing them against ground movement data. So here's an example, again, just mapping some of each of those indices. We can map onto a network, produce a set of maps like this. So for each pipeline, we can say what the information is that the water utility company already has, but also what the information is that the satellite data is providing. And then we can throw all of that into machine learning algorithms to prioritize maintenance. And we've found a lot of power in using plots like this. I'll try and talk you through this. This is called a gains curve. And essentially what we're doing here is thinking about what percentage of failures can we prevent by repairing certain percentages of the network. So for example, if we replaced 20% of the network, if we did that completely randomly, we would expect to prevent 20% of failures. If we use, in this particular example, if we use just InSAR, and 20% of failures, we'd expect to do identify about 50% of the failures. So we're improving. We've got an improvement factor of 2.5 or so. If we use the customer data in this location, the customer's doing slightly better with their information on things like the age of pipes, soil conditions. But if you combine the two together, you do even better. So at 20%, you end up preventing about 70% of failures. And actually, of course, it gets much more interesting in the bottom left-hand corner, because in general, companies are not in a position where you can be replacing 20% of networks. So if we just look here at the bottom left, where we're talking about the bottom 1% here, what you can see there is that the InSAR data by itself and the customer data do pretty much equally well, but the combination does something like 40% better than just using the customer data. And that was something we found in a number of different test cases. Those kind of multiple tens of percents of improvements in our ability to identify pipes that would go on to fail. And the way this works, of course, is we're using test data sets, keeping them quite cleanly separated from the training data sets. and trying to do this analysis. And we had a lot of help, a lot of work, particularly with Northumbrian Water on that, which was extremely helpful. So this is something we're going to be hoping to roll out more routinely, and I'll talk a bit more about that in the context of our follow-on demonstration project that we're currently working on with ESA. So we do have other ways that our work and our data we think can be useful for water utility applications. For example, in infrastructure monitoring. So this is a dam in England, and you can see again these coloured dots in here, and you've got these are two different geometries. You can see this blue dots here and red dots here, and that's because we're looking at slightly horizontal in different directions with these two different data sets. But what you can see is if you look at the time series here for points on the dam in this location or in this location, you've got periods where it's moving fairly steadily and other periods where it accelerates a bit more rapidly. And from this is obviously really important and useful data for the water utility companies. What we're doing with one of those companies already, as the service we're now rolling out, is a continuous kind of monitoring and alerting system. So essentially, we look at all of these individual points, and we can work with a customer to understand when they would like to be alerted, how much movement would be a concern to that customer, and so we can then provide automatic alerting. So if we process the data and there's been an excursion beyond a normal range for that point, we can provide an alert which might then trigger a site visit from an engineer. And of course, we'd expect this to be integrated within a full solution of other monitoring data sets as well. Where we don't have coverage, I mentioned earlier that we don't always have good coverage in natural vegetated areas. What we can do is install corner reflectors. So these are essentially a cube with the sides cut off. And the idea is here, if the radar energy comes in, it bounces off all three faces and goes straight back to the satellite. You get a very, very bright, very powerful measurement that dominates all of the background signal, and you can make very precise measurements on those individual points. And we have a bespoke design that's tuned for Sentinel-1, with a number of designs where we can either look at individual satellite geometries or multiple geometries to try and measure those ground movements. And we have several of those trackside with Network Rail, for example, and been talking to some water utilities about installing them on dams and other sites as well. So following on from the first phase of the dripping project, we won some funding to actually really evolve that and make it much more operational and much more commercial through a demonstrator project, 2-year project. Our primary partners there are Severn Trent and Northumbrian again, but also Yorkshire Water and Arcadis Gen. And the idea here is that we're going to be integrating our data within systems such as the systems built by Arcadis Gen to provide information on likelihood of failures, but also to try and better quantify the value of the data. And so we'll be rolling out a number of products, some of which might be dashboards to look at individual bits of infrastructure. Some of it will be these working further on developing this risk indices and ranking approach. So we're very excited to be just starting that this month. So just to summarize, I think I've covered a very broad overview very quickly of some of the things we're doing that's hopefully been of interest, and hopefully we'll have some plenty of time for questions. But we can do historical assessments and provide data on any scale, really, from small local sites to entire countries. We can work with all the available satellite data, both open access systems such as Sentinel, but also commercial systems such as the Italian Cosmo SkyMed system or the German TerraSAR-X system. We're able to do ongoing monitoring and alerting, identifying areas that have moved more than expected. And I think in this context, I think particularly valuable potentially to the pipeline community is this ability to be able to rank the relative risk of individual sections of pipeline that can help then either target preventative maintenance, or indeed help when pipelines are installed, making sure that they're installed with appropriate materials, etc. We have a range of data analysis tools, simple web-based systems. We have you can get that data straight into ArcGIS or QGIS systems. You can also we have an API that allows you to access our data into your own system fairly straightforwardly, and that's very flexible. We have a very smart team working on that who can help create bespoke tools that are what you need. And we do a lot of automated and bespoke reporting, as well as have people in-house who understand the data, who can really look at it and provide that detailed expert view of the data, what it means, and what it means for that particular piece of infrastructure. So I will leave it there, and I'm happy to take some questions. So I'm not sure whether people are typing them in the chat. Okay, I see some in the chat already.
Yeah, we've got a couple in chat. If you want to start from those in, I can read those out. Can you see them?
Yes. Okay.
Perfect.
Yes. So I guess question one: when you use AI to correlate indices to InSAR data, how do you verify the AI's conclusions and check the failure mechanisms postulated? So what we're doing is we're taking a training data set. So we take some information on known failures, and we use some of that for training and some of that for testing. So that's the general mechanism. What we'd like to do is be a little bit more. One of the things we're excited about in the future work is not only being able to just look at sort of time averaged failure information, but also to be able to do more dynamic prediction. So we can say, based on the recent data, maybe incorporating features like what the weather conditions have been like, being able to produce kind of dynamic forecasts as well. But the essential idea is to make sure we're very careful about separating out the test data and the training data, so that we can actually test how the AI is doing. Because I think all of these systems, it's rubbish in, rubbish out, right? So you need to have good training data, and you need to be looking at it in a kind of critical way. And I'm sure our technical team will tell you that's probably one of the most annoying things about Andy and me, is that with our academic backgrounds, we do tend to be very untrusting in results. So we are very, very careful about checking these things before we roll them out. There's another question here from Ricardo Donati. So InSAR can monitor ground movements, but it doesn't work if resolution cells change significantly. Can I clarify? Yes. So the way InSAR is working is, if you imagine the radar signal coming in, it's bouncing off individual scatterers within a pixel. So a resolution cell. So for Sentinel-1, that's a patch of ground about 5 by 20 meters. Now, in some of those cells, all of the energy comes back from one point. So if we put an artificial reflector in, it all comes back from that one point. In many others, it comes from a distribution of pixels, of reflectors within that, scatterers within that resolution cell. Now, provided most of those scatterers stay in the kind of same configuration and don't change their properties, then we get a useful signal. But so they can, if the whole pixel moves, that's fine, and we track that movement. If, say, you've got 10 scatterers and 1 or 2 or 3 of them get disturbed, then you'll probably still get a useful signal. But the more of those that get disturbed, the worse that we get. And there's different kinds of disturbance as well. So some things are temporary disturbances. So you can imagine monitoring a mountain, and in the winter there's snow on there, and in the summer there isn't. So what you can do is you have to skip the periods of snow, or if you're monitoring a town and maybe on one occasion somebody's parked a very large lorry next to your building. So that just changes the scattering properties. But the algorithms are designed such that if it's a temporary loss of coherence and these scatters are temporarily disturbed, we can recover the signal. But in other cases, if it's a field, for example, and you had those 10 scatterers were stones within the pixel with it, and then the field gets ploughed, those all get moved, and we can't get a useful measurement. So a lot of the effort in the algorithm, a lot of the cleverness in it is about identifying the good pixels from the bad pixels and separating those out. Hopefully that sort of answered that question. Okay, what's next? Some more here. Next one from Daniel Me. Have any trials been done around risk failure on gas network assets? I think we haven't done any work with gas utilities. We'd be very happy to. And if you wanted to set something up, we'd be happy to talk about that. I think intuitively it feels like it's a similar kinds of problem to water, and the same kinds of ground movement should be similarly problematic. But we haven't looked at that yet, but we'll be happy to. Then we have a question on the effect of ground movement on water quality. For example, whether ground movement could increase pollution in groundwater sources. That's a very good question. What we have done and seen in a number of different countries is there are places where groundwater is extracted for use. Obviously, we do that in the UK a lot, but in places like India, it's unmanaged and unregulated. So you get it has been historically, it has been. I think there's been movements to improve that in recent years, but you get some very significant areas of subsidence due to water pumping. It's not quite the same as pollution, but I think I could imagine a situation where you could use this data in conjunction with knowledge of the groundwater system and the hydrology to combine that to help build a model that would help you understand pollution. And then a question about LiDAR. So can your data be combined with LiDAR, and would this be beneficial? Yes, is a short answer. So LiDAR, typically LiDAR is flown from aircraft, sometimes from drones these days. So it tends to be surveys are kind of more one-off. So what you don't have is these regular long time series. But we've been doing some work with one of the things we've done with Network Rail, for example, is they do repeat LiDAR surveys. Typically, there might only be 2 or 3 LiDAR surveys for an individual area, but you can look at that. You can look at how the ground is moved from the LiDAR data and combine it and compare it to the InSAR. The LiDAR often has a higher spatial resolution, which is good, and it's also has different sources of noise. So it's you're able to get rid of vegetation in some cases with LiDAR, and that can be helpful. So sometimes we're getting measurement points with LiDAR where we wouldn't with other systems. The other way we've been using LiDAR is we've been doing some work on flooding at the moment, just a bit of R&D that's currently underway, looking at the radar data and actually looking at those. We talked earlier about whether the reflection characteristics have changed through time, the scatterers have changed. One of the ways they might change is if you had flooding, obviously where you had scatterers in the field or in the town, those are going to change their properties because of the flooding of the water. As well as that, you also change the brightness, the amount of energy that comes back to the satellite. So we've been looking at combining all of that information to try and understand flood distributions using these radar images. And one of the things we found there, of course, we've got in the UK very many places, most of the UK now has a nice environment agency LiDAR data, so that can provide some additional kind of sanity checking when you're monitoring flooding. We're expecting the flood water to be fairly flat, typically. So one of the things you can do is combine the InSAR data with the LiDAR to very accurately determine the height that the flood water reached at the time of the radar acquisition, for example. So I think that's exhausted the ones in the chat. Are there any other questions either in the chat or anyone who wants to come in and ask a real life question? Yeah. Okay, can we elaborate on the studies we did for Northumbrian? Yeah, so it was essentially this work where this was the work we did with the comparison of the machine learning test, essentially. So this is where we took several areas of data, and forgive me, I forget exactly which areas we used for the testing, but what we did was we took those areas and we again used some training data and developed these AIs. And what we did it separately. We did it in-house, and Northumbrian did their own analysis using their own systems as well, and they broadly gave the same answers. So it was encouraging, and we're hoping to, with the funding we've got from ESA, to roll this out into something that will actually save more money for the water utility companies. We did some sort of back of the envelope. It's quite hard. It's always going to be statistical. One of the things we thought about is how do you quantify how much money, how much is, this is a kind of commercial questions I'm been less used to dealing with as an academic, but how much is the data worth to somebody? And if you've prevented a failure, prevented a pipe burst, how do you prove that? How do you quantify the saving? And in the end, it has to be kind of statistical. So you have to look at these kind of statistical tests and say, well, we think we're doing 40% better by using the InSAR data than we were without. We're replacing this many pipes, so that's going to give us a certain number of preventions. And then those, of course, some bursts are don't cost very much to fix, and some are extremely expensive. And so trying to understand the statistics of that, it's not an easy problem to solve, but the bottom line was it does save money if we can get this working.
No, thanks for that, Tim. Can I just kind of mention, I mean, that was my question, in fact, so just I wanted a bit more certainty as to what direction the other water utility companies are taking in predictive kind of technology that they're using for monitoring pipe failures, basically in networks, whether it's wastewater or water. Yeah. So I'm from Southern Water, Virendra Chulan. So we are looking kind of at various technologies now, kind of how we can get some more kind of traction into that field, because as you know, with weather pattern changing and kind of if we can kind of predict in advance on our rising mains and our pipeline networks, how we can predict those failures in advance, that would be fantastic. And it's great to see. I mean, thanks a lot for your presentation. I mean, that's the first I have seen, in fact, with this technology. So to be good to explore. So just kind of on the Northumbrian and you mentioned Severn Trent as well. Yeah. So are these kind of these studies done? Are they available, or can those be shared, or whatever work you have done, so to speak, so we can take similar direction, for instance, or what you have learned?
That's a good question. I think I'm not exactly 100% sure of the exactly what can be shared, but we can take that away and come back to you and have a look. I think because it was done in the context of research project, I think it can largely be shared.
Hi Tim, it's Joy McKenny, Northumbrian Water.
Oh, hi Joy. How are you?
So I worked with SatSense on the project they're describing, and Virendra, if you want to get in touch with me, and we'll see what we can share. So
fantastic.
I'll put my email address in the chat.
Brilliant.
No spam, please.
Great.
And I think we're also looking for extra partners on dripping. I think it's not too late to join that project. And I think with this technology, we're all learning, I think, still about the best way of applying it and how to maximize the use. And we made quite some progress with Northumbrian. But again, it could quite be different in different regions, different geologies. I'm fully expecting the showing the London clay, the shrink swell problem is going to be one of the major causes of pipe failures, and that's something we've been really targeting in the last few months to try and really improve the ability to pull out that information from the data, for example.
Yeah, no, it was interesting as well, just to add to that, kind of when you mentioned about the pipeline conditions as well can be integrated as part of the analysis, and your kind of the hit rate is much better with that. Yeah, that's fantastic to see that. And how do you do that? How much data do you need, and what sort of data?
Yeah, so I think again, Joy would be good to answer some of this as we've got her on the line, and she did some of the analysis in-house. My colleague Tom Ingleby did that within SatSense. I don't think he's on the call, but I think typically we'd want information on historic failures on kind of hundreds, I think, of sites to be used for the training. As many as you can, but obviously leaving some behind for test areas. I think we did it geographically with Northumbrian. We took one area that we used for training and another area that we used for the testing. And I think there's, as I said, a number of tests still to be done. I think, Joy, if you got any further comments on that, would be really helpful.
Okay, right. I think what we did from memory, and it's been a while since I've looked at it, we used data, I think, from 2015 up to roughly 2018. I think 3 years of training data, and then we held back the 2019 data that we knew what the results were. So when Tim talks about training data and test data, that's how we did it. We did it chronologically, I suppose, or temporally. And then so we created our model based on the holdout sample, and then tested and how did it form at predicting the bursts in, I think, our Essex and Suffolk region in 2019. And that's how those gain curve graphs were created to show how good the model was at picking out bursts in 2019.
And these are pressure variation, or are you looking at pipe thicknesses, conditions, and the like?
So the model that we have that already existed looks at lots of different pipe characteristics. I think there was 20 or 25 different characteristics of the pipe, and the standard ones like age, material, soil, and then we added lots of other ones, anything that we thought would be useful. And then when we had something useful, then we added the SatSense data on top of that to see what difference it made.
Good. Thanks for that, for sharing.
You're welcome.
Yeah. And I say that can be, we're very flexible, whether that's done with existing in-house models like the model I had at Northumbrian, or whether we do that, the similar algorithms we can apply within SatSense as well. So it can work either way. And one of the things we're also trying to do is we're working with Arcadis on their tools. I think are quite useful for this financial modelling aspect as well. So hopefully that will be a new development in the next year or so. I saw there was another question. Is it possible to perform subsurface monitoring of assets based on ground movement and compare data against data from pipeline inline inspection tools? I guess we are restricted to movement of the ground surface. So if there's a failure underground that doesn't cause ground surface movement, then we wouldn't see it. So yeah, so I think that's the short answer to that. I think many the places where it's useful, most useful probably are going to be where it's the clay shrink swell, it's subsidence due to mining or land slippage, or somebody's built a new construction nearby and that's caused some subsidence or heave. Those kind of processes are where the data is probably most useful. The cases where, I don't know, a tree root goes through a pipe, maybe harder to pick up. We might see ground movement after the failure, so there might be cases where there's failures that then cause ground movement, and I guess there may be some cases where that can be useful if it's not picked up on the ground. But I imagine a lot of these are picked up before the satellite. I can see a hand up as well, Chris Mencuti.
Yes, thank you very much. I asked the first question on AI, and your answer was very helpful.
Thank you.
But these are looking at populations of data. Just building on this last question you've answered, I wondered if there were cases where you looked at the surface ground movement you're seeing from InSAR, perhaps then inferred the pipe deformations and bending, and including the assets condition to look at the limiting strains and the imposed strains and the risk of failure, i.e. looking at trying to predict and understand the mechanisms better, perhaps on individual high-profile cases, to verify or augment the population trends that you're looking at with AI. This is my question.
Yeah, I think that'd be great to do some of that. We haven't done that at the moment. Everything we've done so far on the pipelines has been statistical or with these AI type techniques. But I think, you know, if there are some really good case studies where these movements are known, and it would be great to work with people with the expertise in the mechanics of the pipes and the failure stresses, etc. It would be really reach out. We'd be very happy to work with you. I think it was a good example you had.
Okay, thanks. Because we do a lot of assessments and so on. I suppose at the predictive stage, and it would be good to see how it interacts with this sort of continuous monitoring capabilities. Yeah.
Excellent. Thank you. Okay, I think let me go back to the chat in case there's anything else there, but I think that's all. Okay, should we take this as the last question? I'm conscious that it's approaching 1 o'clock, and again, strict instructions. We make sure we're over by 1. Is your resolution sufficient to monitor movement of an above ground section of a pipeline? I guess it depends. So it's the short answer on exactly what the process is that's causing the movement, scale of the pipeline, the depth of the pipeline. So it's not going to be 100% solution for every single problem. But obviously, where you need high resolution, we can get the commercial high resolution data sets. Some areas we pre-process. Some areas of London we have that available, but most of the country we don't have that pre-processed, so that ends up being a lot more expensive, unfortunately. Okay. Right. Well, I think thank you for your attention. Yusuf, have you any wrap-up words or anything else to add?
No, that's great. Thank you for participating. Thank you so much for joining the presentation. Thank you for all the questions at the end. If you have any further questions or you want to get in touch, we've got our email there that Tim's just popped in, contact@satsense.com, or we'll send around our email addresses after this alongside the slide deck if you want to have a run through it. But it is a really exciting sector. And we'd be excited for kind of some work off the back of the dripping project that we're currently doing, and kind of any other work that you think our data would be useful for. So yeah, please get in touch, and thank you so much for joining.
Great. Thanks everyone.
Cheers.
Thanks for your time.
Bye.
Thank you very much. Cheers. Bye.